Welcome. In this particular talk we're going to have a look at a couple of different aspects about collision avoidance. In particular here we're trying to determine how that we can predict or detect that a collision is going to happen in the near future, and then based on that we can trigger some appropriate avoidance behaviour. So, collision avoidance, we to date have looked at a couple of forms which are related. So whenever we were considering the steering behaviours, we had a separate behaviour, and it looked at the surrounding objects, worked out if any of them were sufficiently close, and then tried to move apart from them. The forms that we're going to look within this are a little bit more sophisticated. They're going to be concerned about how an object is travelling, and is only if its direction of travel is going to result in a collision that it would be detected and then some action would be taken. So in this sense you could, for example, have two cars that are very close to one another, but if they're travelling in parallel, travelling in the same direction, there's no risk of a collision based on their current direction of travel. So whether or not you want to take action to avoid a collision, of course it depends on the physical locality, but it also depends upon how the objects are moving relative to one to another. For the games that we're looking at here, a lot of this assumes that we are simply detecting that a collision is upcoming. Often for the avoidance element, we're going to use one of the steering behaviours. So this is very much sort of a delegate form of behaviour, that we will detect that a collision is imminent, and then we will pass off appropriate information, for example to a flee or to a separate or to some type of behaviour for a steering algorithm that can then change the position and the velocity and acceleration of the object so that the collision is avoided. So fundamentally in this talk it is really detecting that a collision is upcoming, and then the response very often will be in terms of using steering to move us apart. If we think about how do we detect that a collision is likely, what we need to think about, as mentioned, is the position, is the velocity of the objects. And you can see on the diagram here we have two objects, sort of a green and a blue object, and they have two directions of travels as indicated by the arrows. And as they proceed along those directions, there will be some point in the future where they will get as close to each other as they are going to get, and that is what we want to detect. That's the 2 points we want to work out, because based upon how big the object is, or how big the two objects are, that will determine if they are sufficiently small that they can pass through that point of closest return and not hit each other, or if they are larger than the separating distance, then they are going to crash into each other. The comment at the bottom is quite relevant, that if we're thinking about how close the points get, it isn't simply projecting their velocities and looking at where the two velocities cross over in terms of the overall direction the objects are travelling in, because how close they get depends upon the speed of the object. So if the green object was moving quite slow and the blue object was moving quite fast, by the time the green object crosses over the path that the blue object's been following, the blue object could be way ahead in the distance. So we just can't simply look at where the paths cross. It has to be a more sophisticated calculation, taking into account how quickly they're moving along those particular paths. So let's do it. It requires a little bit of maths to work this out, but it's a fairly nice, fairly elegant component. So I mean, it's one that can be used for a range of different types of activities. We're assuming here that we've got two objects, 1 and 2. P1 and P2 is the position within our game world of our two different objects. V1 and V2 are the velocities with which object 1 and object 2 is moving through our world. If we want to work out the time of closest approach, so this is when, based on the current velocities that we have, how long needs to elapse before the objects are as close as they are going to be. So we haven't yet worked out the point, but if we know the time, then we can plug that in based on the velocity and work out where it will be at that time in the future. So the time of closest approach is shown as displayed on the screen. We have two vectors, a dp and a dv. We'll introduce these in a second. We're taking a dot product between those, and again we'll talk about that in a second. And we are dividing it by the magnitude of dv, and that particular magnitude squared. So let's look at the different terms to see what they are within this equation. So dp is position 1 minus position 2. It effectively is the relative separation of the objects. Makes sense if we're thinking about, okay, do we have a collision? What really matters is how close the two objects are to one another. So dp is simply the separation, if you like, from object 1's perspective. How does object 2, how far away is it? dv is velocity of object 1 minus velocity of object 2. It is their relative velocity. So we're calculating a relative position and a relative velocity. And again, that makes sense. The relative velocity, basically you would imagine yourself being one of the objects, looking at the other object in terms of how far away it is, and you know what speed you're moving, you know what speed the other one's moving at. So relative to you, how is the other object moving? Is it going in parallel? Is it heading towards you very quickly? Is it going in a different direction? And these two components, if you think about it intuitively, that's what we're interested in. How far are we apart and how quickly we're going to actually cover that distance. For the dot product, the general form of any two vectors, so a dot b, is shown here. So we effectively, in working out the dot product, we go through our vectors and we take the first component from each of the vectors, multiply it together, take the second component, the third component, the fourth component, many components we have in the vectors, multiply the same component from one vector with the same component from the other, and then add up that total sum. So in a two-dimensional game, where we have vectors with an x and a y coordinate, the dot product is basically the x of the first one, the x coordinate of the first one, multiplied by the x coordinate of the second one, add on to this, the y coordinate of the first one multiplied by the y coordinate of the second one. Very, very quick, very simple to calculate. So it's two multiplications and an addition. You might think, okay, what's the point of that? The dot product actually is an incredibly useful mathematical operator, particularly in terms of computer games development and graphics and a whole host of areas. It gives you a very easy way of working out how two vectors are orientated in relation to one another. And if one of them is of a unit length, like a directional vector, you can then do projections along that particular unit vector. You may want to sort of draw this down on a piece of paper and go through the maths and take a few examples. But one of the characteristics of the dot product is that if you have two vectors which are orthogonal at right angles to each other, then the dot product of one vector against the other is always going to be 0. So two vectors, if they are right angles, orthogonal, dot product always will be 0. If the two vectors are parallel to one another, they're going in the same direction, then when you multiply them out through the dot product, you're going to get a certain value of a certain magnitude. And how big it is will just depend upon, for example, the size of the x's, the size of the y's. That, if you like, is your maximum value. So if they're parallel, you'll get a value. It'll be as big as values you can get for those two vectors. And all the other values in between, if it's 89%, against if it's almost parallel, if it's 45 degrees, they will give you a value in between. So effectively, taking the dot product lets you work out, for these two vectors, if they are pointing in the same direction, if they're more or less pointing in the same direction, if they're right angles to one another, how aligned the two vectors actually are. And in this particular case, if I have a particular separation, so I'm imagining myself standing here, the other entity that I'm trying to work at if I'm colliding with is directly to my right, so say along the x-axis. But my velocity is along the y, the other velocity is along the y, so we're moving parallel to one another. There we have two vectors that are orthogonal, and the dot product would be 0, so we're never going to collide. If it's the other way around, where each person's pointing towards one another, then they are closing as quick as they can, and in that sense you're going to have a large positive dot product as they are approaching one another. So dp.dv gives us an indication of just how quickly, using the relative velocity, is the relative distance going to be covered. How long does it take to cover that particular distance? Dividing it by dv, so this is the relative velocity. If you take the magnitude of that, it's the relative speed, the closing speed if you like, and squaring it. This effectively gives you then the time of closest approach. Given that particular time, we can then plug that into the equation. So we know that P1, or item 1 is at position P1, moving velocity V1, and at our calculated time value, that's when it's going to be as close as it's going to be. So we can work out what that position actually is, and do the same for the second object too. A little bit of a side, you can actually get negative values from doing this here. And what does a negative time value mean? What basically it means is that the two vectors are, the two velocities are divergent. They are not approaching each other, they're actually separating from each other. So a value of -2, for example, would mean that it was 2 seconds in the past, based on these velocities, that the objects were as close as they were going to be. And other than that, they are actually divergent, moving apart from one another. A positive value means that there is a degree of closeness. The vectors are actually closing towards one another, and then yes, you do have some time of closest approach. Once you have detected that a collision is going to happen, so that's looking at the size of the objects and the positions of the closest separation, then you want to detect some action, probably based on that. If the time of closest approach is 30 seconds in the future, you may not want to do anything. If it's 2 seconds in the future, you probably do want to do something. Something like evade or separate, they're all good behaviours then to trigger in that particular case. And quite often it makes more sense to trigger it using the points of closest approach as opposed to the current approach. So you try to avoid where the collision is going to happen, as opposed to trying to avoid the object wherever it is currently at the current point in time. A little aside here that it is theoretically possible, it's very unlikely, but it is possible that whenever you work out the 2 points, point of object 1, point of object 2, you'll sort of end up with 2 points which are utterly identical. That, depending on the steering behavior you can put in, doesn't give any separation between them, because there is no separation, it's 0. So you just need to take that into account in terms of your steering algorithms to make sure that you have a special case for reacting appropriately. If we were to express this as a chunk of pseudocode, we have something that looks as follows. So we've got a collision avoidance algorithm. We're passing in our source object, which is trying to detect if any collisions are upcoming. And we've got an array of things that we potentially want to avoid. They could be other moving objects, they could be static objects, but there's sort of small objects that we want to have a look at to say, okay, do we need to do anything about this? We are going to have our closest target and our closest time. Initially, closest target is null if we don't have anything that we're approaching. Closest time now, if there are multiple objects and we're going to collide with a couple of them, then we're interested in identifying what's the first one we're going to collide with. We better react to that before we're worrying about a later one. So initially our closest time, we set it to as large a value as we can get. We've got a closest step and closest distance. We'll use those values. Determine the closest target then. So this is the bit that will work out, well, what of these objects or targets values that we have here, which one am I likely, if any of them, to hit or in the near future. So go through each object. We work out its relative position and its relative velocity, so it assumes we have position and velocity vectors available within our objects. We're working out then the relative speed and also the relative distance, so sort of taking just simply the length of the two the vectors in terms of the velocity and the positions. We're then carrying out the actual equation to work out the time to collide, and this is where we use our dot product. I'm taking the dot product of those two relative vectors and dividing that by the magnitude of the velocity, which is the speed, squared. Having done that then, we can work out what the minimum degree of separation is. So how close they will get is equal to the relative distance, how far they are apart, and we're going to take away from that the relative speed times the time to collide. So relative speed times the collide, that's going to be how close we're going to get. We take that away from relative distance. That will give us our minimum separation, just how close do these objects approach. The if after that then checks to see, well, do we need to worry about it? So if the minimum separation is less than the size of those two objects combined, and here we're assuming that they have circular bounds, which is easy and makes sense in this particular case. So adding, for example, the radius of the two items. If our minimum separation is less than that, then we'll have a collision. And then we check to see, okay, time to collide is greater than 0, so this was something that is going to happen as was to happen in ocean in the past. And if the time to collide is less than the closest time, so in other words, this is the first collision that we've detected, or the collision is going to happen soonest. At that point, we then store the closest target and the closest time. So we're updating those. These are the ones that, once we've edited through all of our objects, will contain just how many seconds we have before we're detecting a collision and just how close we're going to be in terms of that collision. So we'll call that. We have a check here to see, do we have a closest target? It's possible that we could actually be diverging, going in a different direction from all of those things. So we may not have a closest target, something we're going to potentially collide with. In that case, we return null. If we do have something that we're interested in, then we're doing a check here just to work out if we want to evade on our current position, or do we evade on the sort of the target position where we think the collision is going to happen. So that takes into account just how close the collisions are, and is it more appropriate to evade on the point of the collision or simply to evade where the current object is. It's a screen's worth of code. It's not overly complicated, but it does actually quite a very good job in terms of detecting and then reacting to, if using evade, upcoming collisions. Having looked at how we can detect collisions for sort of moving objects, they're generally assumed to be small objects. I mean, they can be static, they can be moving, but they're generally assumed to be small. We want to have a look now at how we can detect potential collisions against large objects. For large objects, we've got a bit of a problem. Well, it depends how you bound them. We were assuming spheres in the previous one, and you probably don't want to take, for example, a wall or a large object and simply bound it within a sphere. So quite often for our large objects, we want to maybe skirt around them, to plan out, and sort of the proper pathfinding algorithms will come in here about how you navigate your way through an environment. Most common way of handling large objects within an environment is to use ray casting. And this actually is very similar to what we were doing with the velocity. We were imagining the velocity traveling it forward. In this case, we're doing something similar. We're taking the direction of travel of the object and we're casting out a ray of a certain length. If you like, this is the length of this ray is the visibility, how far ahead the object actually can see. And we're going to be testing that against all of the geometry that we have within our particular game, all of the big things that we want to try to avoid. We're assuming here that if our ray hits something, we will then be able to return or to work out the point at which it hits it, and also the normal. So I've given you an output vector that is at right angles to that particular surface. If I have the point, if I have the normal at that point of collision, I can then actually project a point a little bit out from it, so a little bit away from it. And that gives me a point that is close to where I'm going to hit, but it's out from that. And I then change my seek behavior so that I seek towards that particular point. So the object we're not going to crash into the wall, we'll sort of skirt around the wall or run parallel to it. So it works quite well in that sense. If we were to express this as a fragment of code, and it's going to be a small fragment of code, but there's hidden complexity within this. In particular, it's within our collision detector. So it assumes that we have an object that we can pass in a ray that will work out if that ray collides with anything, and if it does collide, that it gives us back information about the point of collision, the normal at that point of collision, and stuff like that. And that's a complicated object, depending on your geometry, to create. So we're assuming a lot of the hard work is being done in some other object. We're simply using that collision detector here to use ray-based avoidance. So we're calling the method, passing in our source, we're passing in a detector. We've got a few things in terms of the avoidance distance, how far out do we move, how far ahead are we looking in terms of ray projection. We create a ray. The ray is based on the direction of travel of the object. So we look at its velocity, we normalize it, that gives us a unit vector of length 1, and that's our direction in which we're traveling. We then scale that up with our look-ahead distances, how long we want the ray to be, otherwise stated, how far in front of the object is it able to detect it's going to collide with something. We have some collision information. So collision information that we're assuming here is an object maybe containing a point and a normal and stuff like that. And we go to our detector and we say, okay, for this current position, here we have a ray being cast from it. Does it collide with anything? If it does, give me information. And if it doesn't collide, then we're saying, okay, there's nothing more to be done, we'll simply return. If it does collide, then what we're using is the position of the collision with the normal and our avoid distance to give us a new target away from the object that we will seek towards. So at this high level, very straightforward, but the complexity in this is in terms of writing the collision detector. If you want to get a few other sort of links to good sources, you can see them here on the screen. There's a massive amount of stuff on collision detection with different sort of shapes and geometries and ray casting. So it's a large, quite interesting area. If you have an object where you're only casting out one ray from it, that's fine. It's a little bit limiting in that because you only have one ray, it's not taking into account the size of the object that's trying to move. And you can see an example over here where we're casting out the ray from the center. We're saying the ray spine is not hitting anything, but we're moving reasonably close to, in this case, like a wall, that as the triangle is moving forward, it's going to collide against. So casting one ray has its limitations. We could get around that by, for example, casting rays from the extremes of the objects, the different sides. And that would mean that we would detect the collision with the wall and the side above. There's, again, a downside about this that is known as the corner trap. And you can see that in the example, or sort of the right middle of the screen, where you may have one ray saying, oops, I'm going to hit a wall, turn to the right. And the other ray on the other side saying, oops, I'm going to hit a wall, turn to the left. And the turn to the right, turn to the left, the two behaviors from the rays effectively cancel one another out, and it just then careers straight into the wall. You could also have, for example, one long central ray looking out, and then sort of two smaller side whiskers, really just sort of to detect if there's any upcoming changes in the near vicinity. So you're casting 3 rays, a bit more expensive than this one. Works quite well, but it's hard to go down a corridor, a passage that is quite narrow, because the side whiskers, depending on how far they're projected out, can sort of collide with the wall and stop it moving down. Whiskers only, in this sense you have 2, but they are sort of more in the middle, and they're going out, so you can detect these. Again, not a bad configuration, but there is a bit of a blind spot in the middle that you could again wander into something without actually seeing it. So by way of one key takeaway, if we're looking at casting rays in front of the objects, that actually gives us quite a capable way of detecting collision. Could be with other objects, could be with large pieces of geometry within our level, with walls, with other things. So it's, again, quite a powerful way of working out or querying what lies ahead. You may or may not want to put it within your game. A lot of things we're looking at, some of the space-based ones that could be useful for that, but actually quite a lot of the basic steering behaviours, they also do things like separate, do a reasonably good job as well.